Okay, so we are moving on to section 2.2. So we've been doing a bunch with limits. You guys know last chapter was all about limits. This is kind of the last section where you're going to have to deal with this, and then it really does go away, you guys, and everything gets a lot easier. So we're just going to hang tough here, and we're going to do this a couple more times with the limit process. So we've talked about the derivative before. Just as a reminder, the derivative, okay, is the slope of the tangent line at any point. Okay, so it's the instantaneous rate of change. And so this is the formal definition of the derivative. This is how you can find the derivative of a function, right? So you're given a function, this here, notation, this little prime we talked about is the derivative, and you're going to find that through the limit process, this last section, okay? And then it's all going to get way easier. You have already been given an alternate form from before, and it told you that f prime of c, okay, is equal to the limit as x approaches c of f of x minus f of c over x minus c. This is the derivative at some point c. This is much more common, okay? This is really the one you want to focus on and use. And this is this is just a complicated version of y2 minus y1 over x2 minus x1, okay? And so I'm going to pause here and give you a graph to kind of show you again what the derivative is doing. So what the derivative is doing is if you are here at an x value and you have this function, and then if I come over here to x plus h, obviously this distance would be h here. This is f of x, and this point is f of x plus h. Okay, so to keep this simple, think about a line that goes through those 2 points. You could find the slope of that line as y2, or f of x plus h minus f of x, over x2, x plus h minus x. Okay? If we're looking for the derivative, we're actually looking for the slope of a tangent line here. And so in order to do that, we use calculus. We're going to take the limit as h goes to 0. Well, think about what that is, you guys. This distance here is h, right? If this is x and this is x plus h, if we send the h value to 0, what you're doing is you're moving this guy back here towards this point. And so this point comes all the way back here. It gets so ridiculously close that you really are finding the derivative at that point. And so all we have to do is take the limit as h goes to 0 of the slope through those 2 points right there, f of x plus h minus f of x, all over x plus h minus x. The x has disappeared, you just get h. That is the formal definition of the derivative, okay? All right, so how do we use it? I'm really not going to hit this a ton on the test, okay? You've got to be able to do it at least once. And so what we're going to do is we're going to find f prime of that function using this formal definition, okay? So the derivative at x is going to be the limit as h approaches 0 of, okay, f of x plus h. So you're going to take x plus h, you're going to plug it into the function, and you get the square root of x plus h. Then you're going to subtract the whole function itself, which is just the square root of x, and you're going to put that over h. Okay, so all we did is we plugged into this formal definition of the derivative. Now, the reason this is chapter 2 is because you wouldn't know how to do this without chapter 1, right? So I'm assuming that you're comfortable now with the limit process. We talked in chapter 1 about direct substitution, plugging in 0, you would get 0 over 0. You obviously have to do something here. That would be rationalized, right? You have square roots. So we're going to multiply by the square root of x plus h plus the square root of x, all over the same thing, square root of x plus h plus the square root of x. And so this conjugate helps us because when you FOIL this out, you get x plus h. Outside and insides go away. Minus, that just becomes x, right? All over h times the square root of x plus h plus the square root of x. Okay, that's helpful because the x's cancel. And then your h's would cancel, leaving you with the limit as h goes to 0 of 1 over what's left, which is the square root of x plus h plus the square root of x. And as h goes to 0, direct substitution leaves me with 1 over the square root of x plus the square root of x, or 1 over 2 of those guys. Okay? And so the derivative of that function is that. All right. What does that mean? That is the derivative of the square root of x function. So what does this do? It tells me the slope of the tangent line at any point. Okay? All right, so this limit process is cumbersome. Okay? You basically have to plug in this stuff here and then go through your limit process and get there. Now, I'm going to do a little preview here just to remind you and to show you how easy this is going to get. In the next section, there's going to be a rule. It's called the power rule. And let me show you how easy this is. If you have a function, okay, f of x, and let's say it's equal to x to some power of n, the derivative using the power rules, right, these cheats or these shortcut derivative rules, instead of the formal definition with the limits, all you have to do is you bring down your exponent, you multiply by the x value to one smaller power. Okay, and so let's use that to verify what we did here. Okay, so we started with the function f of x is equal to the square root of x. Well, we know that that is x to the 1/2 power. Hopefully you know that. Okay, and so let's find the derivative using this power rule. It's really easy. You take your exponent, you bring it down in front. So you bring the 1/2 down. You keep your variable x, and you raise it to 1 smaller than what we had. Well, if you take 1/2 minus 1, you get negative 1/2. Okay, and when we simplify that, you have 1, the 2 is downstairs, x to the negative 1/2 comes down to the denominator, and you end up getting the derivative. Okay, so I do this, right, with calc students because this is right where you guys start to get super frustrated. Hopefully chapter 1 test went good. Okay, but if it didn't, right, this all seems like a lot of algebra and work, and it is. Okay, but once we get past this section, this limit process goes away, and we start learning simple rules on how to take derivatives. And it really is, this entire problem, right, is right here. Okay, what I want you guys to focus on is that is the derivative of that function, and this tells me the slope of a tangent line to that function at any point. Okay, so thinking about the square root of x function, hopefully you guys know it looks like that, something like that. We'll go out here to an x value of 4, right? At x equals 4, plug it into the derivative. F prime of 4 would be 1 over 2 square root of 4, which is 1 over 2 times 2, or 1/4. What does that tell me? That is the slope of that tangent line. Okay, so the derivative tells me the instantaneous rate of change of a function at any point I want. I chose to look at 4, and I know the instantaneous rate of change is 1/4. Okay? All right. So until the next lesson, we're going to keep practicing this limit process. So let's come down here to the next example. It says, look, find f prime if your original function is x cubed. Okay, this gets super messy because of all the algebra. Okay, but using the power rule, let's cheat so that we know where we're going. The power rule says bring this down, bring this 3 down, times x to 1 smaller, and then the derivative of a constant is just 0. And we'll get into that tomorrow with the rules. But you could think of negative 1 as negative 1x to the 0, right? Because then 0 times that will go away. So either way, we know using the power rule that this is what we should get. Now let's do some nasty algebra to make sure we can do it. So using the formal definition of the derivative, we're going to take the limit as h goes to 0 of f of x plus h. F of x plus h is plugging in x plus h everywhere there's an x. So I have x plus h quantity cubed minus 1. That is f of x plus h. Minus f of x, which is just x cubed minus 1, all over h. Okay, a lot of people mess this up at the beginning. So let me just make sure you guys get that. If f of x is x cubed minus 1. Remember, f of 1 would be 1 cubed minus 1. F of a would be a cubed minus 1. F of x plus h is x plus h cubed minus 1. Okay, and this is the one that we're using here. So that's how I got that. You're just taking a function and you're plugging this in to the x value. You're cubing it and you subtract 1. Okay, all right, so now let's do all the ugly math here. So we're gonna rewrite this as the limit as h approaches 0. X plus h cubed is x plus h times x plus h squared, which hopefully you know is x squared plus 2xh plus h squared. Okay, then we have our minus 1, don't forget that. And then we have minus x cubed plus 1 all over h. Okay. All right, so little things happen here. These ones go away, so that's nice, but let's do this disaster. So this is the limit as h goes to 0. Let's take this x and let's distribute it to everything. So I get x cubed plus 2x squared h plus xh squared. Now let's take our h value and we get plus x squared h plus 2xh squared plus h cubed. And then over here, the ones went away, so all I have is minus x cubed all over h. At any point, you guys could have plugged in direct substitution and plug in 0, and you would have got an indeterminate form. So all we're doing is we're using this same exact process from chapter 1 where we're trying to continue until this doesn't blow up and give us indeterminate. So let's see what happens here. Our x cubes go away. That's great. And then we've got a lot of stuff left over here. But every single term has an h in it, right? So now I have the limit as h goes to 0. Let's take an h out of the upstairs stuff, and I get 2x squared plus xh plus x squared plus 2xh plus h squared all over h. And that helps us because these h's go away. And let's take the limit as h goes to 0. Well, as h goes to 0, that guy goes away. That guy goes away. That guy goes away. And so I'm left with 2x squared plus x squared, which is 3x squared. Lo and behold, all of that, okay, all of this terrible algebra could have been done with a simple rule that we'll start using maybe towards the end of this section, but next section for sure. So just keep your eye on the prize, you guys. You got to get through and be able to do this once. Okay, it's just like a rite of passage with calc, and then we're going to forget about this limit process and use all these rules. Okay, so if you come over here, it asks you to graph both of these. It's obviously going to be a lot cleaner if I can just graph it here. So let's go in here and graph the original function, which is x cubed minus 1. And then let's graph the derivative, which we found to be 3x squared. Okay, and we're going to graph it on the same coordinate axis, and we're just going to look for some things. Okay, so as you graph that, okay, you can see here that this blue line was the original function, and then the red line is the derivative. Okay, the red function, if the derivative is above the x-axis the whole time, okay, and the reason it's above the x-axis the whole time is because think about a slope of a tangent line right here. It would be positive. And then tangent right there would be positive, and tangent right there would be positive. And then what about right there? Wouldn't my tangent line be 0? That's why the derivative value is 0. And then all of these tangents are positive. Okay, and so we're going to do that in this next problem with our graph. Okay, so every year in calc, there's particular things that students really like and don't like. This is usually one that's kind of hard in their brain at the beginning, but the more familiar you get with derivatives, this gets easier. You are not going to be asked to graph by hand the derivative of a function on the AP exam, but you could be asked on a multiple choice style question to pick it out. Okay, and there's some really easy things to do here. This is the graph of f. If you're going to try to graph f prime, okay, think about slopes of tangents. Slopes of tangents. That's what the derivative is, right? Derivative is the slope of the tangent line. Well, what about this tangent line right there? Isn't that slope 0? That tells you that f prime, which is the slope there, is 0. And so if I'm going to graph f prime, I know that it's equal to 0 right there at -2. Same argument right here f prime is 0. And so at 1.5, I know that my graph is going to cross at an x value of 0. Okay, now let's think about all these tangents. Positive, 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 positive. Every single tangent line up to that point is a positive value. And down here, it's like positive 20, positive 15, positive 10, positive 1, positive a half. And so your derivative graph comes down towards this to be 0. And in between here, every single tangent line is negative. So in between here and here, every function value of the derivative is negative. Okay? And then from here on, all of these are positive slopes. And they're getting more and more positive, right? Like right here, it's positive 1, and then it's positive 2, and 3, and 10, and 20, and 50. And so this thing goes up. Okay? That is not easy to do the first time around, and you will get better at this. Okay? And once we learn our rules, I think it'll make even more sense. Okay, let's get into the next page, which will go a lot quicker. So up here, we're talking about places where the derivative, right? This is really important. The derivative does not exist. Well, what's the derivative? The derivative is the slope of a tangent line. We'll go to an absolute value function. What's the slope of the tangent line right there? We don't know, right? The tangent is there and there and there. This derivative right there, f prime, does not exist because we don't have a unique tangent line. What happens here? This is called a vertical tangent. Well, what's the slope, right, of a vertical line? We know the slope is undefined from algebra 1. Well, the slope is the derivative. And so right here, if you have a vertical tangent, your derivative is undefined. Same argument here. This is called a corner. This is called a cusp. They don't ever ask you that vocab on the AP exam. Don't worry. You just have to know right there f prime does not exist. How come? Because there's not a unique tangent line. Okay, so that's just some visuals of the derivative. All right, so determine if f prime exists. And then that's it. I guess it just wants to know, does it exist? My definition here, my hint says use the definition of the derivative. Let's not use the definition of the derivative. Let's use the power rule, which you haven't even learned yet. I've kind of told you about it. It's very simple, okay? And we're going to use that to save ourselves a lot of time here. So let's write f prime of x is equal to, and let's take the derivatives. So let's talk about that power rule again. The power rule says take the power 2 and bring it down as a coefficient. Well, if there's already a negative 2 there, it's 2 times negative 2, which gives me negative 4. Then I rewrite my x value and I raise it to a degree of 1 less than what it was. Well, 2 minus 1 is just 1, right? And then I'm just going to write this out because we're doing this for the first time. The derivative of a constant is 0. There's lots of ways to think about that. You could think about this as 4x to the power of 0. And then when you bring the 0 down, it makes it go away. You could think about y equals 4 being a horizontal line. And what's the slope of a horizontal line? 0. So the derivative is 0. So this becomes plus 0. All right. Over here, you bring down the 2 times x to 1 smaller. Okay. And your domain constraints stay the same. So that happens when x is less than 1 and here when it's greater than or equal to 1. So we have a piecewise function, and now we know that the derivative of those pieces are these. Well, let's just take the limit, just like we did before. The limit of f prime, though, not f, as x approaches 1 from the left. So I plug in, I get negative 4. And let's take the limit of the derivative as x approaches 1 from the right. Well, from the right, I plug in 1, and I get 2 times 1, which is 2. Okay, therefore, what do we know? The f prime at 1 does not exist, okay? Because the limits don't equal each other, okay? Think about it this way. You're going to go from a line here that's negative 4x. Well, we know what that looks like. It's a line with a slope of negative 4. And then at 1, I'm going to switch over to a positive slope line like that, okay? And what happens there? That's no good. Does not exist. Okay, so determining if f prime of 1 exists, okay, is taking the derivative of a piecewise function just like we did before and doing exactly what we did when this was not prime. You're just analyzing the limits. If the rate of change coming in from the left is negative 4 and coming in from the right is positive 2, that's not matching up. Therefore, the derivative does not exist there. All right, and then this last question, it just says, given some function f, it models the number of people in a football stadium in thousands, right? What does this mean? This is the rate of change, okay, of some value is equal to 35. All right, so some function models the number of people in thousands, where t is the number of hours after noon. So that is 3 p.m., right? The number of hours after noon. So you would say the rate of change of the number of people in thousands at 3 p.m. is 35,000. Okay, and it's a positive number, right? So if f is a function that models the number of people in a football stadium, f prime of 3 equals 35 tells you that the rate of change at 3 p.m. is 35,000 people, right? A lot of people are showing up to this stadium at 3 p.m. Okay. All right, this is just a theorem here. Differentiability tells you that something is continuous. So if I tell you if f of x is, I'm going to abbreviate that, differentiable, okay, then f of x is continuous. So all that stuff we did before, proving continuity, if somebody tells you that a function is differentiable, you know it's continuous, okay? The other way is not true, but we'll get into that at a later time. All right, guys, take care.